You want to purchase a laptop. Will you simply walk into a store and pick any laptop? It is highly unlikely. You would probably browse a few web portals where people have posted their reviews and compare different laptop models based on their features, specifications, and prices. You may also ask your friends and colleagues about their opinion. In short, you would not directly reach a conclusion. Instead, you will take a decision considering the opinions of other people. Similarly, in supervised data mining, the objective is to build a model that can explain the relationship between inputs and output. The model can be considered a hypothesis that can map new input data to predicted output. For a given training set, multiple hypotheses can explain the relationship with varying degrees of accuracy. Ensemble methods or learners optimize the hypothesis finding problem by employing an array of individual prediction models and then combining them to form an aggregate hypothesis or model. These methods provide a technique for generating a better hypothesis by combining multiple hypotheses into one. Since a single hypothesis can be locally optimal or overfit a particular training set, combining multiple models can improve the accuracy by forcing a meta-hypothesis solution. Ensemble models have a set of base models that accept the same inputs and predict the outcome individually. Then the output from all of these base models are combined, usually by voting, to form an ensemble output. Ensemble methods are used to improve the error rate and overcome the modeling bias of individual models. They can produce one strong learner by combining many weak learners. The diagram shows the framework of ensemble models. You will be able to take advantage of combined decision-making power only if the base models are good to begin with. While meta-learners can form a strong learner from several weak learners, those weak learners should be better than random guessing. Since all the models are developed based on the same training set, the diversity and independent condition of the model is difficult to accomplish. While complete independence of the base models cannot be achieved, you can take steps to promote independence by changing the training sets for each base model, varying the input attributes, building different classes of modeling techniques and algorithms, and changing the modeling parameters to build the base models. In order to achieve the diversity in the base models, you can alter the conditions in which the base model is built. Take a look at the most commonly used conditions. Different model algorithms. The same training set can be used to build different classifiers such as decision trees using multiple algorithms, naive Bayesian, k-nearest neighbors, artificial neural networks, etc. The inherent characteristics of these models will be different, which yield different error rates and a diverse base model set. Parameters within the models. Changing the parameters like depth of the tree, gain ratio, and maximum split for decision tree model can produce multiple decision trees. The same training set can be used to build all the base models. Changing the training record set. Since the training data is the key contributor to the error in a model, changing the training set to build the base model is an effective method for building multiple independent base models. A training set can be divided into multiple sets and each set can be used to build one base model. However, this technique requires a sufficiently large training set and is seldom used. Instead, you can sample training data with replacement from a dataset and repeat the same process for the other base models. Changing the attribute set. Similar to changing the training data, where a sample of records is used for building each base model, you can sample the attributes for each base model. This technique works when the training data has a large number of attributes. Voting ensemble can be considered as the simplest of all the ensemble learning methods. This model is an ensemble learner that houses multiple base models inside the inner sub-process. All these models accept the same training data set for model building, and then the test data point is passed through each, thus receiving an individual output from each of them. For example, a training data set can be passed through decision trees, k-nearest neighbor, and support vector mechanism. The output of this can be used for predicting new values. The act of tallying all the predictions of these base learners and providing the majority prediction is the job of the meta model, the vote model. This is also called the aggregation step in ensemble modeling. The model output from the vote process behaves like any other classification model, and it can be applied in any scenario where a decision tree can be used. Bagging is a technique where base models are developed by changing the training set for every base model. In a given training set T of n records, m training sets are developed each with n records by sampling with replacement. Each training set T1, T2, T3 and so on Tm will have the same record count of n as the original training set T. Since they are sampled with replacement, they can contain duplicate records. This is called bootstrapping. Each sample training set is then used for a base model preparation. Through bootstrapping, you have a set of m base models, and the prediction of each model is aggregated for an ensemble model. This combination of bootstrapping and aggregating is called bagging. Bagging is particularly useful when there is anomaly in the training dataset that impacts the individual model significantly. Bagging provides a useful framework where the same data mining algorithm is used for all the base learners. However, each base model differs because the training data used by the base learners are different. Since each base model explores a different solution space, the performance of the ensemble model would be better than that of base models. Boosting offers another approach to building an ensemble model by manipulating training data similar to bagging. As with bagging, it provides a solution to combine many weak learners into one strong learner by minimizing bias or variance due to training records. Unlike bagging, boosting trains the base models in sequence one by one and assigns weights for all training records. The boosting process concentrates on the training records that are difficult to classify and overrepresents them in the training set for the next iteration. The boosting model is built by an iterative and sequential process where a base model is built and tested with all of the training data. Based on the outcome, the next base model is developed. In the beginning, all training records have equal weight. The weight of a record is used for the sampling distribution for selection with replacement. A training sample is selected based on the weights and used for model building. The model is then used for testing with the entire training set. Incorrectly classified records are assigned a higher weight and correctly classified records are assigned a lower weight. Therefore, hard to classify records have a higher propensity of selection for the next round. The training sample for the next round will most likely be filled with incorrectly classified records from the previous round. Hence, the next model will focus on the hard to classify data space. Boosting assigns weight for each training record and has to adaptively change the weight based on difficulty of classification. This results in an ensemble of base learners specialized in classifying both easy to classify and hard to classify records. When applying the model, all the base learners are combined by a simple voting aggregation. Recall that in the bagging technique, for each iteration, a sample of training records is considered for building the model. The random forest technique uses a similar concept to the one used in bagging. When deciding on splitting each node in a decision tree, the random forest only considers a random subset of all the attributes in the training set. To reduce the generalization error, the algorithm is randomized in two levels: training record selection and attribute selection in the inner working of each base classifier. Take a look at the steps through which the model works. If there are n training records with m attributes, and k is the number of trees in the forest, then for each tree, number 1, an n random sample is selected with replacement. This step is similar to bagging. Number 2, a number d is selected where d is much less than m. D determines the number of attributes to be considered for node splitting. Number 3, a decision tree is started. For each node, instead of considering all the m attributes for the best split, a random number d attributes are considered. This step is repeated for every node. Number 4, as in any ensemble, the greater the diversity of the base trees, the lower the error of the ensemble. Once all the trees in the forest are built, for every new record, all the trees predict a class and vote for the class with equal weights. The most predicted class by the base trees is the prediction of the forest.